Good morning. Well, that's good.
I'm confused.
Okay, let's see if I've got this. Yeah, I'm not muted. So, okay, let's see if this is going to work today. Okay, we are going to be talking today about pregnancy and development. And we finished up the repro section. You may notice that we have our hearts over here for this section this afternoon. Hopefully it's a little more solid than that by 1 o'clock. I never seem to guess right on when to thaw them out. So, but we'll see. Take it on a microwave later on. So, what? We have a microwave. It's not for human food, not for human foods anyway. So, okay. Female reproductive physiology. We've always assumed, and I was taught this, and I taught this for a long time, that the total number of eggs that a female would have is determined at birth. conventional wisdom was somewhere around 1 million or so eggs at childbirth when the female baby is born, and about 400,000 or 500,000 by the time puberty starts, or somewhere in that neighborhood. That's the conventional wisdom that's always been around. Now, it is entirely possible that just like the stem cells in the seminiferous tubules, just like the stem cells found in the seminiferous tubules, we can also have stem cells on the outer layer of the ovary that produce new eggs. It was thought that all the eggs that a female would have all the eggs she's ever going to get at childbirth when she's born, and then whatever she has at puberty is what she's going to get left to ovulate. And while she has 400,000 or so eggs, she's only going to produce about 500 eggs over the course of her reproductive years. But then that number starts going up when you consider that every month an egg is ovulated. Every 28 days an egg is ovulated, so that's 13 eggs ovulated a year. But there's usually a half a dozen eggs that come with that until the dominant egg is selected. So there may be more than just 500. Maybe there's 5,000 or 6,000 eggs that are used. But the conventional wisdom was that if a female got pregnant at age 40, she got pregnant with a 40-year-old egg, which meant there was a greater potential risk of some sort of birth defect or malformation in the baby, because it was an old egg, because eggs wear out. But not if a 40-year-old female is pregnant with a brand new egg. That's all, and everything, all the previous assumptions are wrong. So we don't know yet, but it's a possibility that we're going to discover in another 10 years or so that perhaps there are stem cells in the ovaries that are producing eggs, just like the stem cells in the seminiferous tubule that produce the spermatogonia. So we'll see. Anyway, moving on. Oogenesis and spermatogenesis. We've talked about spermatogenesis. Spermatogenesis occurs from the spermatogonia. On the inside lining of the seminiferous tubule, you have the spermatogonia, the A and B cells, and the A cells stay there as stem cells, and the B cells ultimately become immature sperm cells. Spermatogenesis, the creation of sperm cells, gives you 4 viable haploid sperm cells for every spermatogonia. Pretty straightforward, pretty simple. Oogenesis, the creation of an egg, is different. You get 1 egg produced per oogonia, and you have 3 what we call polar bodies. So we instead of producing 4, we only produce 1. Oogenesis gives you 1 egg and 3 polar bodies, because we're going to do something with the excess chromosomes. But the polar bodies, all they are the leftover chromosomes. All the nutrients go into the 1 egg. Now, there's a significant difference here in the mistake rate. We call it the error rate, but mistake rate sounds better. Spermatogenesis has an error rate of 3 to 4%, meaning you can produce sperm cells. What that means is the sperm cells didn't divide properly. You may get a sperm cell carrying 2 X's instead of an X and Y. It may contain 3 X's. It may contain an XYY. It may not contain any of the sex chromosomes. See, because remember, males, the sex chromosomes in the male are X and Y. So the male sperm are going to either be X or Y. Now, what happens if a sperm is produced with nothing in it. That's a mistake. Or no, or nothing in it here. And that sperm happens to fertilize the egg. Then you end up with an egg that is X0. Okay. Viable, but it does have its own issues we can talk about later. Now, the error rate is in spermatogenesis is only 3 to 4%. So that means 96% of all sperm cells made are going to have either an X or a Y. It's that 3 to 4% that might have a combination of, might have this. So if an X and a Y, if that happens to fertilize the egg, because the egg is always going to have an X. So if an X and a Y fertilize that, you're going to get an X, X, and a Y in there. Not out of the realm of possibility. 3 to 4% out of 400 million is a lot. I'm not going to try to do the math, but that's a lot. But it's a whole lot more that don't have any errors in it. So anyway, but in oogenesis, the error rate is 20%. There's a 20% chance when an egg is developing in the ovary that it can have a mistake, have an error in it, some sort of mistake. Now, in the egg, you can have all sorts of combinations. You can have an egg. The normal egg has an X chromosome, but you can have double X, triple X. You can have no chromosome here. There's all sorts of combinations that can occur. So just like in the sperm, you can have two Y chromosomes. You can have an X and a Y. Any combination of mistake that you can think of will occur. Okay. So, but because you're only producing one egg, see, because spermatogenesis gives you, one spermatogonia gives you 4 sperm cells, but in oogenesis, you have one oogonia gives you 1 egg. So you have less room for error in here. So, okay, the ovarian cycle, 28 days. We start counting the day of the first day of menstrual flow. That is the beginning of the cycle in the ovary, and ovulation is whatever day the egg is released. We can count that. That always becomes the 14th day, because from the point of ovulation to the end of the ovarian cycle is 14 days. So we have 2 parts to the ovarian cycle. We have the follicular phase, where the vesicle, where the follicle that surrounds the egg is growing. And then we have the luteal phase. Name that after the corpus luteum. Since ovulation is day 14, the egg is gone. The Graafian follicle that ruptured to release the egg becomes the corpus luteum. It secretes progesterone from day 14 to day 28. Doesn't matter how long the follicular phase is, but the luteal phase is always 14 days from ovulation to the end of the cycle. Doesn't matter if it was day 17, it becomes day 14. Doesn't matter if it's day 12, it becomes day 14. Because the amount of time to get from ovulation to the end of the cycle is 14 days. Now, how many women have a perfect 28-day cycle? What's it say? 10%, 15%. Most women are going to have a variable cycle. And it can be different every month. There's no rule that says it has to be exactly 28 days. The only consistency is we know from ovulation to the end of the cycle is 14 days. So lots of people vary. We also know that the ovaries don't alternate left and right, left and right. It may be all one side, maybe all the other side, and maybe 3 months here and 2 months here, and then back and forth. So there is no rule that says we have to go left ovary, right ovary, left ovary, right ovary. So here's what happens. In the follicular phase, the first 14 days, you have follicles. Now, a follicle is a bubble. You know, it's a bubble surrounded by follicular cells with something inside of it. We call them the vesicular follicles. So this is a bubble, and within the bubble is the egg. Now, what causes this follicle to grow is the release of FSH, follicle stimulating hormone. Imagine that, it causes follicles to grow. Follicle stimulating hormone released by the anterior pituitary. And you'll see that in the female, the follicle stimulating hormone will continue to be released from the anterior pituitary up to about the 14th day. What does this do? Well, there are always a cluster of follicles maturing every month. And so you have a cluster of follicles ready to go every month, and they start maturing. But only one out of that cluster becomes what's known as the dominant follicle. We don't know why it's the dominant follicle, but it becomes the egg of the cycle, egg of the month, if you will. So it may be a half a dozen follicles are all maturing, ready to the point of being able to ovulate the egg, but only one becomes the dominant follicle. So here we see what's happening. FSH in the red line, FSH, as soon as we hit the follicular phase, FSH is being released from the anterior pituitary. Its numbers go up, level off, and then drop down again. And then right at the point of ovulation, it spikes and then drops way down. Luteinizing hormone is going to be the trigger for ovulation. Luteinizing hormone, the one line in blue, stays fairly low and then spikes at the 14th day, triggering ovulation, and then drops way down again, also sort of parallels the FSH. We don't need luteinizing hormone and follicle stimulating hormone in the last half of the cycle. Why wouldn't we want to have luteinizing hormone and FSH in the last half of the cycle? What does FSH do? FSH brings along another follicle. If you have released a follicle at ovulation in the middle of the cycle, you don't want to have another one coming along. And so luteinizing hormone levels drop, FSH levels drop, because there's the anterior pituitary says, oh, there's no reason to release another egg yet because we've got this one in place. And what's telling it that there's another egg already there is the corpus luteum is secreting progesterone. Progesterone levels are high, and that tells the anterior pituitary we have an egg already. We don't need to bring another one along. So that's why we don't allow one to mature. We ovulate on the 14th day, and nothing happens again till the next 14th day, because the second half of the cycle is all about the corpus luteum. Yeah.
So what exactly? Because I know that when you undergo like fertility treatments, it raises the likelihood of like local. So how exactly does that happen? Like, how does that raise
Okay, good question. What happens is that the fertility drugs are a combination of probably estrogen, progesterone, and FSH. And the FSH stimulates more follicles in the first 14 days. It brings more eggs to maturity. See, because normally what will happen is when when a female ovulates, she ovulates one, maybe two, like very occasionally 3 eggs. Very unusual. You know, it's nearly always one, sometimes 2. But because the dominant follicle containing the egg is selected over all the others. For whatever reason, it is the best of the follicles there. So we get 1. But if we are saturating the ovaries with additional FSH, which is what you get when you have the hormone therapy, you're going to bring more eggs along. Now, they still may only ovulate 1. So at this point, you generally have to harvest and let's they call it harvesting the eggs. And you got to do it before ovulation occurs because then the rest will be disintegrated. So you got to get them early on, before the luteinizing hormone is released. So the reason that in vitro gives you such a high birth number is because you pull out as many eggs as you can get that are all mature, and then you expose them to sperm and semen, and you don't know which one to fertilize, and maybe they all fertilize. So you just try to implant the batch and see what takes. And sometimes you get 2 or 3, sometimes you get 1, sometimes you get 8, and they all are viable. So, and that's why the synthetic FSH is stimulating so many more eggs. So, okay.
And how does, one more question, how does, like, when identical twins, like, how exactly does, like, how does it decide that it's going to split? Does it just, like, split? Or, like, is there a...
Don't know.
Okay.
All we know is that identical twins come from 1 egg that splits in half. It undergoes mitosis and splits into 2 separate developing babies. Whereas fraternal twins, you have to have 2 eggs. And there's no guarantee that 2 eggs are going to be released at the same time, because it's entirely possible to have 2 separate eggs and 2 separate fathers. That happened just recently, a couple of years ago. A woman had sex with 1 man, and that fertilized 1 egg, but unknown to her, she had released a 2nd egg. 2 days later, she had sex with another man, different man, fertilized that egg too. So now she's carrying 2 viable offspring from 2 different fathers, simply because of her choices on when she was going to have sex and with whom. They're different.
And it can that also apply to women who are born with multiple uteruses?
Oh yeah, that could happen too. That's unusual, pretty rare, but it can happen. Yeah, there isn't much that can happen. The simplest explanation, though, in this case, was she just had sex with 2 different men, a day or 2 apart, and had 2 viable eggs. So that's statistically, that's pretty unusual for that to happen. The multiple uteri is probably statistically probably about as common as the other approaches, the approach that she took. So it probably got pretty exciting at delivery. We'll just let it go at that. But it happens. Just about anything like that can happen. So, but there are going to be cases of a woman with a multiple uterus. I mean, dogs and cats happen. How do you think you get so many dogs or cats in a litter? Because you have the X number of uteri in there. So, okay. So we see the follicle stimulating hormone levels drop. They spike at ovulation, and they drop way down again, because now we're moving into the luteal phase, where the corpus luteum takes over. The corpus luteum is the old the follicle that contained the egg. It ruptured, and now it's going to start secreting progesterone. And before I go on, progesterone is what keeps the lining of the uterus intact for 14 days. Now, the term oogenesis, how long does it take? Well, actually, it's years. The production of an egg starts in utero. The oogonia are the stem cells. So just like in sperm cells, we have where we have the spermatogonia, the diploid stem cells, we have the diploid ovarian stem cells in here, and they are going to be producing something called primary oocytes. Now, what happens here, this is where we get into meiosis, which is nuclear reduction. We want to produce an egg, a viable egg that is haploid, because the sperm cells are going to be haploid. But to get there, we start laying down eggs in the ovaries while the female baby is in utero, and they're going to produce oogonia. Now, here's the thing about these oogonia. The oogonia are all diploid. So what's happened here? The oogonia, these stem cells, developed through oogenesis in the fetal stage. The oogonia are all going to be diploid, and there's going to be thousands and thousands of these oogonia in the ovaries. Oops, there we go. Now, the oogonia are going to become what are known as primary oocytes as they grow. They're still diploid. They're still containing 46 chromosomes. They undergo DNA replication, and they go into meiosis, and they stop in prophase 1. So here we are. We have this egg, this oogonia, this primary oocyte that has formed in the ovary, in utero, and it's at some point it goes into prophase 1 and stops there, and it will stay there suspended in prophase 1 until the onset of puberty 12 years later. From the time it becomes from the time the oogonia goes into meiosis while it's in utero to the time it starts, when it goes into prophase 1, it will stay there for 12 years, whenever puberty starts. The numbers suffer from time. These primary oocytes, most of them break down. At birth, a female has about 700,000 oocytes. At puberty, that's dropped to about 400,000. We used to say several million at birth. Now it's down. Now the numbers are more specific. It's 700,000. The 400,000 has stayed pretty consistent. A female, as she enters puberty, will have about 400,000 of these primary oocytes. The primary oocyte is still a diploid oogonia. Every month, some of these after puberty starts, every month, some of these primary oocytes are stimulated by FSH. Now remember, they're all stuck in prophase 1. Meiosis, if you remember, has the same stages as mitosis: prophase, metaphase, anaphase, telophase, but it does it twice. So you have prophase 1, prophase 2, metaphase 1, metaphase 2, and so on. So all these primary oocytes are stuck in prophase 1. Every month, a handful of them are stimulated by FSH. Out of this handful that gets stimulated, one becomes the dominant follicle and gets to continue meiosis. The rest just disintegrate. So at the end of meiosis 1, you end up with 2 cells. We started out as a diploid cell. Now we're a haploid. We have 2 haploid cells. We have what's called the secondary oocyte. It has all the organelles. It has all the cytoplasm. It has 23 chromosomes instead of 46. And we have a polar body. So here we are at the end of meiosis when we have the dominant follicle. Dominant follicle has been selected out of all of its friends. You know, this cluster of primary oocytes are being saturated with follicle stimulating hormone. One became the dominant follicle. We don't know why. Maybe it was the healthiest. The dominant follicle then will complete meiosis 1 and give you a secondary oocyte. It was a primary oocyte. Now it's a secondary oocyte with 23 chromosomes, all the cytoplasm, all the organelles. It'll give you a polar body, a little tiny thing off to the side. That's the polar body. The secondary oocyte starts into second meiosis, but it stops at metaphase 2. So the secondary oocyte that gets ovulated is going to be stuck in metaphase 2. And if nothing else happens, it stays stuck in metaphase 2. If it's fertilized, and fertilization occurs not when the sperm penetrates the cell membrane, but when the 2 nuclei fuse, the nucleus of the sperm and the nucleus of the egg fuse together, that is fertilization. So when fertilization occurs, then meiosis 2 will continue. Because the secondary oocyte, the primary oocyte the dominant follicle is selected. The primary oocyte inside the dominant follicle is going to start meiosis 1, and it goes through meiosis 1, but it stops at prophase 1 and nothing happens. Go back and say that again. The primary oocyte undergoes meiosis 1. When we get through, let me state this one more time. Okay. The primary oocyte that has formed during utero undergoes meiosis 1. It's a diploid primary oocyte. It stops in prophase 1 and stays in prophase 1 until puberty. These primary oocytes, there are 400,000 of them. Every month, a few of these are saturated with FSH. One becomes the dominant follicle. A follicle and an oocyte are 2 different things. The oocyte, the egg, is inside the follicle. So the follicle can enlarge. The follicle can grow. We have a follicle that becomes the dominant follicle. It is selected by all this FSH being poured on it. And the dominant follicle each month will finish meiosis 1. Remember, it started meiosis 1 in utero, and it stops at prophase 1 and stays there till puberty. At some point during puberty or somewhere, those primary oocytes are continually exposed to FSH, and one of them completes meiosis 1, and that gives you the secondary oocyte and a polar body. Now, the secondary oocyte starts meiosis 2, but stops at metaphase 2. And that's what gets ovulated. A secondary oocyte is in metaphase 2, the second stage of meiosis. If fertilization occurs, then the secondary oocyte completes meiosis 2 and kicks out another polar body. But and so the haploid secondary oocyte is going to fuse with the haploid sperm cell. If fertilization doesn't occur, the secondary oocyte degenerates. So our primary oocyte is formed at the end, is formed when we go into prophase 1. It stays there until puberty, when we have a dominant follicle completes meiosis 1, and then we get the secondary oocyte. The secondary oocyte is what gets ovulated. No guarantees it's going to be fertilized. Secondary oocyte is stuck in meiosis in metaphase 2 until if it gets fertilized. So we have the primary oocyte and the secondary oocyte. We had the oogonia, became the primary oocyte, which became the secondary oocyte, which gets ovulated. The follicle is a vesicle surrounded by follicular cells with the oocyte inside. We start out with a primordial follicle, which is what we find in our fetal stage. The primordial follicles, we have a primary oocyte, probably stuck in prophase 1, surrounded by one layer of cells. That's a primordial follicle. And this is what we see in the female ovary up through childhood before we get to puberty. Oops, didn't mean to do that. There we go. There we go. So here we see a primordial follicle. One cell layer of follicle cells with a primary oocyte inside. The follicle and the oocyte are two different structures. It's easy to get this confused, trust me. At puberty, FSH causes a change in the primordial follicles. The follicle once it's exposed to FSH, the primordial follicle becomes the primary follicle. And then when it becomes a primary follicle, it continues to grow around the primary oocyte. Okay. Now we have what's known as a secondary follicle because it's got multiple layers of follicular cells around it. There's our oocyte inside. We have two layers. Now we have what's known as the zona pellucida and the zona granulosa. These are just we have multiple layers of follicle cells now around the oocyte. The secondary follicle, as it continues to be exposed to FSH, will continue to grow. The primary follicles will continue. One is selected to be the dominant follicle. It becomes the secondary follicle or the Graafian follicle. And we produce two layers around the egg. We have the zona pellucida, and we have let's see, how did I say this correctly? There we go. The zona pellucida and the zona granulosa are the layers that form around here. Now, those are going to come to play later on during fertilization, because the sperm cells have to get through the zona pellucida and the zona granulosa here. If our follicle has continued to mature, it is the Graafian follicle or the tertiary follicle. Some textbooks use a different term than Graafian. So our secondary follicle is the one that the secondary follicle is a primary follicle that has continued to grow and enlarge and lay down multiple layers of cells. The Graafian follicle blisters out on the surface of the ovary. At ovulation, the secondary oocyte is going to be ejected from the Graafian follicle. There's a bulge, there's a bubble on the side of the Graafian follicle. There's what our typical Graafian follicle looks like. We have the zona pellucida and the corona radiata forming. That's why I kept thinking, zona granulosa, what happened to the corona radiata? The zona granulosa is way out here, but the corona radiata and the zona pellucida go with the secondary oocyte. This is what the Graafian follicle looks like. Here's a smaller one over here, getting ready probably for next month. But this is what's going to rupture this Graafian follicle. So if you like flowcharts, and who doesn't like flowcharts, you can see what's happening here. We start out with the stem cell, the oogonia, the diploid stem cell. It undergoes mitosis, and we're still diploid. We have the primary oocyte. The primary oocyte starts at some point, maybe while we're still in utero, while the female's still in utero, or shortly after birth. The primary oocyte starts meiosis 1, but stops at prophase 1 and stays there till puberty. At puberty, the primary oocyte, one of these primary oocytes, completes meiosis 1 and starts meiosis 2. It has become a secondary oocyte, and it stops at metaphase 2. And it stays there until fertilization or until it degenerates. When the secondary oocyte is ovulated, here's the follicle over here. We have the primordial follicle, and we had the primary follicle, the secondary follicle, the Graafian follicle here, and that releases the secondary oocyte, and the follicle becomes the corpus luteum. So this is ovulation. Luteinizing hormone causes the secondary oocyte to be expelled from the Graafian follicle. Luteinizing hormone is the trigger. And the secondary oocyte is contained within its corona radiata. Some women can feel pain. It's called Mittelschmerz pain. Pain on the side during ovulation. Some can, some can't. And my wife can tell me usually one side when she feels it. She can't tell on the other side. That doesn't mean anything. It could mean the other side's not working anymore. Who knows? We see here the numbers are very low for fraternal twins. Only 1 to 2% of ovulations will give you an additional secondary oocyte. So in that example I was telling you about of the woman that had sex with 2 different men 2 days apart, was it 2 ovulations, or was it an ovulation from either side, or whatever? Would it have been it couldn't have been a fraternal twin because it could have been impregnated by the first person. Anyway, doesn't matter. It's unusual, fraternal twins don't happen all that often, but they do, 1 to 2% of ovulations. If both eggs are fertilized and both eggs remain viable and implant successfully in the uterus, lots of things can go wrong. The success rate is not very high for an implanted egg. Now, identical twins, as I answered your question earlier, identical twins come from one egg that has produced one fertilized egg that gives you two identical daughter cells, and then you have, the identical twins. Okay. So after we have ovulation, we go into the luteal phase. The luteal phase is where the corpus luteum takes over. The corpus luteum is going to start secreting progesterone and a little bit of estrogen. The progesterone is what's going to keep the lining of the uterus intact. The uterine lining builds up in the first 14 days of the uterine cycle and reaches its max somewhere between days 14 through day 21. If we don't have a successful implantation, then around day 26 or 27, that lining starts to break down, and by day 28, it's really breaking down and it starts sliding off the next day. And we count the beginning of the menstrual flow as day 1 of the cycle. So this is what the corpus luteum looks like. It's releasing progesterone and a little estrogen. It's what's keeping the lining of the uterus intact for at least 10 days. And then if implantation doesn't occur, then it'll start breaking down. Now, given that it takes the egg 7 days to get to the uterus, so by it doesn't get there till day 21, the corpus luteum is only going to be secreting progesterone till about day 24. So it's a very narrow window for that egg to get there and get implanted and start producing HCG, the human chorionic gonadotropin. The uterus produces that, so that that's what tells the corpus luteum keep making progesterone. Okay, so this is what the corpus luteum does. If everything's working right, if there's been successful implantation of a fertilized egg, then the corpus luteum will continue to produce progesterone for about 3 months, at which point the placenta takes over, and then the corpus luteum on the ovary can degenerate completely. Human chorionic gonadotropin. The corpus luteum depends on this to tell it to keep making progesterone. And corpus luteum will start breaking down somewhere between the 25th and 28th day. It generally stops making progesterone by the 24th day. But if a fertilized embryo does implant, if the baby implants in the uterine wall, in the endometrial layer, it will produce human chorionic gonadotropin. This is what shows up in a home pregnancy test kit. It detects the presence of HCG in urine. HCG stimulates the corpus luteum to continue to produce progesterone. It stimulates the corpus luteum to enlarge. Back to this picture here of the corpus luteum. You see, it's huge. It's probably 1/4 the size of the ovary. Normally, they're about as big as this little structure right here. But what will happen is that HCG stimulates the corpus luteum to grow and to enlarge and continue to produce progesterone and estrogen. And that keeps the lining of the stratum functionalis, it keeps that lining intact. There are progesterone receptors on the lining of the uterus. And as long as they're receiving progesterone, they're not going to slide off. And then after about the first 90 days or so, then the placenta is formed and takes over and continues to release progesterone. The corpus luteum then can degenerate. Okay, now let's move on now. Okay, in the female reproductive system, it is regulated by our hormones. The ovarian cycle is regulated by FSH and luteinizing hormone. The ovaries are always releasing small amounts of estrogen. even before puberty. The reason we do this is that the hypothalamus is monitoring hormone levels in our blood. And as long as a little bit of puberty, a little bit of estrogen is being produced prior to the onset of puberty, that's enough to tell the hypothalamus that there's estrogen present. As long as there's estrogen present, then the hypothalamus will not release those gonadotropin releasing hormones. Remember how the hypothalamus controls the anterior pituitary through releasing and inhibiting hormones? So the gonadotropin releasing hormones, if our testosterone levels are low, we will generate the production of more testosterone by producing more luteinizing hormone. You know, if any of the reproductive hormones are low, the hypothalamus detects it and stimulates their production through sending gonadotropin releasing hormone to the anterior pituitary. It's a multi-step control. So up until puberty, the ovaries are functioning a little bit, producing just a little bit of estrogen. Because if we didn't have the estrogen being produced, what would happen? Your female child would start undergoing puberty at a very early age, because it's the estrogen in her ovaries, her immature ovaries are releasing just enough estrogen to prevent the hypothalamus from saying, hey, we need to really up the production of estrogen and FSH and luteinizing hormone, because I'm not seeing anything. I'm not seeing any estrogen at all. Just enough estrogen to keep the hypothalamus in check. However, what happens now is we get close to puberty, whatever age puberty starts. The hypothalamus becomes, is desensitized to estrogen. So it does start releasing gonadotropin releasing hormone, telling the anterior pituitary, it's time to make FSH, it's time to make luteinizing hormone. And they act on the ovaries. The ovaries then start developing, start going through puberty and start producing the estrogen and progesterone that they will produce every month from puberty till menopause, or menarche, as they say, when it all finally stops. Okay. So in a healthy female undergoing a ovarian cycle, we see that the two hormones that are running through the cycle are estrogen and progesterone during the follicular phase, from up through the point of ovulation. The follicular phase goes up through day 14 of the ovaries, and we see the estrogen levels start climbing up into the point of ovulation. Progesterone stays along the bottom, very little progesterone. At ovulation, estrogen levels drop, progesterone levels rise. And that's that green line there. Their levels go up very high. They'll stay high until there's no HCG to continue to stimulate them. If there's no HCG, the corpus luteum shuts down its production of progesterone on day 24, and the levels of progesterone drop drastically. And then we have the uterus starts undergoing menstruation. The corpus luteum is going to be the driver for menstruation. Corpus luteum, as long as it's producing progesterone in high levels, like it does here up until about day 24, the lining of the uterus is going to stay intact. But if we're not going to get any HCG to tell the corpus luteum keep producing progesterone, it's going to slide off. And that's what's going to happen here. And we see the numbers then, both progesterone and estrogen levels drop. They drop way down as we go back into the follicular phase. So now here we see what's happening with HCG. So HCG gets produced almost immediately at implantation, because if the fertilized embryo takes 7 days to get down to the uterus, that's day 21. It only has 3 more days to start producing HCG before everything shuts down. So what will happen now is we'll see a spike in HCG. If there's successful implantation, we'll see a spike in HCG. And then that will drop about the 3rd month, about the 12th week, somewhere in there. You'll see those numbers drop because now the placenta is producing the progesterone and the estrogen. We don't need the corpus luteum anymore. We don't need the HCG, but this is what keeps the lining intact by keeping the progesterone going for the first 3 months. And then you see after that, then the estrogen levels start climbing, progesterone levels start climbing, and the progesterone will drop right at childbirth. So, okay, so what does gonadotropin releasing hormone do? It stimulates luteinizing hormone and FSH. FSH is going to tell the granulosa cells in the ovary, the granulosa cells that surround the follicle, to release estrogen. Luteinizing hormone stimulates androgens, the same stuff, the stuff that's coming out of the adrenal cortex in the zona reticularis. Adrenal cortex, androgens are produced there. Luteinizing hormone stimulates those androgens to be developed, to be produced. The androgens, which are testosterone, are converted in the ovary by the granulosa cells. So it all comes back to the granulosa cells that surround the follicle. Estrogens produced by the granulosa cells, androgens are converted to estrogen by the granulosa cells. We control the release of these FSH and luteinizing hormone through negative feedback and through positive feedback. One of these few times where positive feedback actually works for us. If the estrogen levels rise, the granulosa cells will release inhibin. Inhibin inhibits FSH release. If estrogen levels go up, a couple things are going to go on here. So if estrogen levels rise, that's going to inhibit the release of FSH and LH. Why do we need FSH and LH? We've got lots of estrogen, so we're not going to release more of it. We're also going to inhibit FSH from the production of inhibin from the granulosa cells. There's only one structure that can withstand this drop in FSH. We have high estrogen, and that shuts down the FSH release. We have a drop in FSH. There's only one structure that can withstand that, and that is the dominant follicle. So for whatever, somehow the dominant follicle is selected, and it doesn't mind the drop in FSH. All the other follicles are going to degenerate. So if there's a handful, if there's a cluster of 7 or 10 or 24 follicles that were being brought along by being exposed to lots of FSH, only one becomes a dominant follicle. That's the only one that can withstand this sudden cutoff of FSH levels. And we go back and show you this chart again. Where'd it go? Maybe I went too far. There we go. See how FSH drops right here? It drops right before ovulation and spikes again at ovulation. This is what eliminates all the other follicles in here except the dominant follicle, because none of them can withstand this drop except the dominant follicle. We don't know why it's the dominant follicle, but it is. Okay, now let's go back. it is estrogen that triggers the luteinizing hormone surge. So while we see FSH levels drop because there's plenty of estrogen, the dominant follicle doesn't pay attention to that drop in FSH. The dominant follicle's granulosa cells can still continue to produce estrogen. The estrogen levels rise, and what this does is, positive feedback enhances the stimulus. So as the estrogen levels rise, it triggers not just the release of more estrogen or FSH, but triggers the release of luteinizing hormone. That spike that we saw on that graph, as estrogen levels go back up, that spike back here, this spike of FSH and estrogen trigger the release of luteinizing hormone. Okay, let's go on. Now, luteinizing hormone triggers ovulation. It triggers the formation of the corpus luteum. The corpus luteum will be active up until day 24 if no fertilization has taken, no implantation has taken place. That's the key, implantation. Doesn't matter if it's fertilized. If it doesn't implant, nothing happens. Luteinizing hormone tells the secondary oocyte to complete meiosis 1. Or rather, it tells the primary oocyte to complete meiosis 1 to become the secondary oocyte. The secondary oocyte will only get as far as metaphase 2. That's what's coming out. The secondary oocyte is stuck in metaphase 2 unless it gets fertilized. So, okay, I said all that already. So now, if no fertilization occurs, the corpus luteum will degenerate because the luteinizing hormone levels drop. It stops producing estrogen and progesterone, which shuts down the stratum functionalis. That lining starts to break down, and the whole thing starts all over again for the next month. A couple of things to bear in mind is that the oocyte is stimulated. The primary oocyte, the dominant follicle, is already selected a year previous. It's only during the last 14 days before ovulation is that dominant follicle matured and ready to go. But it has been pre-selected a year earlier. So if a female is ovulating today, she's ovulating a follicle, she's ovulating an oocyte from a Graafian follicle that was selected a year earlier. So the uterine cycle, 28-day cycle, 3 parts to it. The menstrual phase is days 1 through 5. The pre-ovulatory phase is days 6 through 14 with ovulation on day 14. And then the secretory phase is 15 through 28. First 5 days, the ovarian, the hormones, the estrogen, progesterone are practically non-existent. The gonadotropin levels start to rise because estrogen's low and progesterone's low, and the hypothalamus detects that and says, hey, we need to make some more estrogen and progesterone, so we need some more FSH and luteinizing hormone. So it tells the anterior pituitary, make some more. Meanwhile, the stratum functionalis is sliding off of the lining of the uterus. Remember, the stratum functionalis is the outermost layer of the endometrium, and it separates from the stratum basalis. The blood vessels pinch off, and there is a little bit of blood loss and some tissue loss. And it's a minimal amount of blood loss during the menstrual flow. It looks like more because there's more tissue involved here. Generally by about day 5, it all stops and the ovarian follicles start producing more and more estrogen. The dominant follicle and all of its friends are growing. They're being exposed to FSH. Now, somewhere in that 14-day follicular phase, we're going to see that spike. But right now, while we're in the menstrual phase, we're going to see more estrogen being produced. So this is what's happening in the lining of the uterus. The first 5 days are the menstrual phase. We see the stratum functionalis slide off, leaving the stratum basalis behind. The stratum basalis will start building up the outer layer of the endometrium again during the proliferative phase, and that will continue to climb and grow until we peak out somewhere around the 24th day. That's when we have the maximum thickness of the stratum functionalis. So somewhere in that, generally if there's a fertilized egg to implant, it's going to implant somewhere around the 21st day. And that lining will get thicker and thicker and stay engorged with blood, unless of course there is no implantation. Then the stratum functionalis starts pinching off these vessels, and the blood shuts down to the enlarged area, the engorged area, and those vessels are starting to pop and rupture. And by the end of the 28th day, which is the beginning of the first day, is the menstrual flow. Because ovulation is taking place right here. Now you'll notice that the uterus is not ready yet, not completely ready, because the egg's not going to be there till here. It takes 7 days to get there. And so by the time we get to day 7, we have an even thicker stratum functionalis. 6 through 14 is the pre-ovulatory or proliferative stage. The estrogen levels build up, cause a buildup of the stratum functionalis. The glands enlarge. We start releasing more and more mucus. We have more spiral arteries. We see the stratum functionalis become engorged with blood vessels. There are many progesterone receptors built into the endometrium. Somewhere in this time frame, the mucus in the cervix thins out. And this will continue to build up and continue to build up. The proliferative phase ends at ovulation. Ovulation becomes automatically day 14. At the end of, when we have ovulation, this proliferative phase is over. Then we go into the secretory phase. This always runs 14 days. The endometrium is getting ready for the implantation. Progesterone levels rise from the corpus luteum. The functional layer's mucosa becomes thicker and larger. The nutrients are starting to be released from the endometrium. The mucus layer in the cervix fills up again. We only open up the cervix right around the 14th day. We want to allow the passage of sperm to go through there, and then somewhere after the 14th day, after ovulation, then we start plugging the cervix again. So if we don't have ovulation, the corpus luteum degenerates starting about day 24. Progesterone levels drop. The spiral arteries will kink and break apart. The endometrial cells die. The glands regress into the stratum basalis. The spiral arteries will constrict again, and causing a surge of blood into the capillary beds. And then we have these blood vessels and that surge of blood and the dead tissue sloughing off. And then the day it starts sloughing off is day 1 of the menstrual cycle. So, problems. There is a phenomena called amenorrhea, the sensation of menstruation that occurs in female athletes that if they are engaged in extremely strenuous physical activity, this can alter the female athlete's menstrual cycle. What happens here is that an athlete that has very little body fat, if they are, like a distance runner, like a marathoner, you've all seen marathon runners, how they have practically no body fat. And what will happen in your female athlete, body fat is where we convert androgens from the adrenal cortex to estrogen. No body fat, no conversion of androgens. Leptin involved in diet, hormone involved in diet, and fat production also contributes to the onset of puberty. Leptin tells us what the energy levels are in the female's body. Are they sufficient to allow reproduction? Leptin is a measure of the energy levels. If without enough leptin, then the hypothalamus says, well, we can't start puberty, or we have to shut down the ovarian and uterine cycle because we don't have the energy to support a pregnancy. And so this is a very common occurrence. This sensation of menstruation is a very common occurrence in certain categories of your female athlete, particularly like your distance runners, perhaps your long distance swimmers, things like that. Maybe gymnasts who train extensively, that maintain very, very, very low body fat in here, because we need to maintain some of this body fat. Now, the other thing that can happen is that amenorrhea can also lead to osteoporosis, because we depend on estrogen in the female body to stimulate bone production. Well, we need calcium for a whole lot of other things besides bones. We need calcium for muscle contractions. We need calcium for nerve impulses. We need calcium for our heart to pump correctly. So we're going to rate our bones. And if we don't have the calcium, we're going to get it somewhere. We're going to take it from the bone, and we're not going to build new bone because we don't have the estrogen to stimulate bone growth. Okay. Now, let's see. Okay, let me wrap this up on progesterone and estrogen, and then I want to stop just a little bit early today. So estrogen triggers oogenesis and growth of the follicle in the ovary. It acts on the female reproductive tract, causing it to grow as we hit the secondary sex characteristics. It causes the growth spurts. Stimulates osteoblast activity. The breasts enlarge, fat deposits increase, the pelvis widens. It keeps blood cholesterol down and HDL levels up, and causes the female to take up more calcium. Progesterone causes the change in the cervical mucus. It regulates the uterine cycle. It keeps the uterine lining intact. It also, this is an interesting point here too, is it allows the breast to get ready to lactate. Doesn't stimulate lactation, but it allows the breast to get ready. So it's more than just keeping the lining intact. So, okay. Now, let's stop here. I've thrown a lot at you today, and I want to see if I can't